A very good evening to one and all. I am Dr. Ekta Sarda, Assistant Professor, Department of Computer Science and Engineering, RAIT, affiliated to DY Patil deemed to be University, Navi Mumbai. Welcome you all for AICT sponsored 1 week online ATAL FDP on Geo-AI Innovations in AI for Improved Spatial Data Processing. Approved by AICT, RAIT continues to foster academic excellence and technological advancement and has come up with another program to enhance the skills of the faculty in the upcoming area of Geo-AI. This FDP explores the intersections of AI and geospatial data processing, and this program is designed for the researchers, academics, and professionals seeking to use AI for advancement in fields such as environmental monitoring, disaster management, and urban planning. Now, to give a brief introductions about this faculty development program, I call upon the coordinator of this program, Dr. Prakash Ingula, sir. So over to you, sir.
Thank you, ma'am. Uh, Good evening, everyone. It's my pleasure to welcome you all to this online AICTE ATAL Faculty Development Program on Geo AI Innovations in AI for Improved Spatial Data Processing. This FTP focuses on how artificial intelligence techniques can be utilized in geospatial data processing. To process geospatial datasets, AI driven approaches and capabilities have been proven very useful. So, we thought we could use these two domains together, and so we designed this FTP. This program is structured to provide insights into the research aspects, application aspects, and policy dimensions of GeoAI. Few of the practical applications in using such AI capabilities include disaster management, precision agriculture, and sustainable development and planning. The keynote sessions will illustrate how AI can be useful for disaster response analysis and large scale geospatial data processing. Following sessions will cover the theme of scalable geospatial computations through high performance computing. In the additional sessions, we will explore advanced AI techniques such as deep learning and neural networks, which are used to improve classification and analysis of geospatial data. The session talk on mathematical morphology also will showcase the use of set theory and concepts in spatial data analysis. The application sessions that we have planned to introduce will focus on GIS-based solutions for precision agriculture, offering insights into crop management and agriculture planning. The topics related to synthetic aperture radar also were introduced, which will showcase the advantages over traditional optical datasets. We have also introduced a session on Google Earth Engine, which will help us understand to utilize the online tools for geospatial data. Similarly, we have used applications of the use case of AI algorithms in initiatives like forest cover mapping and sustainability goals, aligning with the priorities of United Nations and is of utmost importance to Ministry of Environment and Forests, Government of India. The concluding sessions also will focus on AI-driven classification techniques alongside with discussions on future trends and policy frameworks shaping GIS in India. This comprehensive approach, we feel, will present the relevance of GeoAI in addressing data processing challenges. We are thankful for the experts from academia and industry, both from India and abroad, who would share their expertise and contributions to this field. We hope that these sessions will be interesting and inspiring to further explore the research in this field. Thank you for joining us, and we wish you an insightful learning experience. Thank you.
Thank you, sir. Now I request Dr. Sangeeta Chaudhary ma'am, convener and head of Department of Computer Science and Engineering, to highlight the importance of this faculty development program.
Yeah. Uh,
Over to you, ma'am.
yeah. Thank you, Ekta ma'am. Good evening, one and all present in this inaugural meeting. Today's chief guest, Professor Durba sir, our principal, Dr. M.D. Patil sir, HOD colleagues, all my faculty colleagues, organizing team, and dear participants. So it gives me immense pleasure to welcome you all for this 1 week faculty development program on Geo-AI, innovations in AI for improved spatial data processing. So as rightly mentioned by Dr. Prakash, this is the blend of geographical information system and intelligence. So we at Computer Science and Engineering Department, we are having the programs in artificial intelligence as well as data science in both UG and PG. And recently we come up with the geoinformatics laboratory. So we thought we were thinking about what kind of topics which we should come up for this FDP. So very apt topic is being suggested by Dr. Prakash and Dr. Digambar, who are the coordinator and co-coordinator. And as he mentioned, this kind of field is giving immense opportunities to provide the innovative solutions to the challenging fields like urban planning, disaster management, and environmental monitoring. And here in this 6 days FDP, all the participants will get the opportunity to listen to the experts who are working in this domain, and they are working in the diverse application areas, as this is very interdisciplinary topic, and lot many things are there. As you have seen, the sessions are varying, from the first session till last session, you will get lot many things. So I request all the participants to take the advantage of this particular opportunity and try to get the fullest from the speakers. And also it is one kind of networking opportunity which we all will be getting, wherein you can get connect with all the speakers who are coming from different research avenues and different organization. So here, without taking much time, I wish all the best to all the participants, and I hope that you will enjoy this knowledge fest from the geospatial domain, and of course the blend of intelligence into geospatial data processing for improved processing in lot many field wherever the spatial data is being used. So once again, I congratulate all the participants for joining this course, and I wish all the best and a fruitful FDP at RAIT. Thank you.
Thank you, ma'am. Now I would like to call Dr. Mukesh De Patil sir, Principal RAIT, to address the participants. He is the driving force behind this institute. Sir has completed his MTech and PhD from IIT Bombay. With the 28 years of dedicated experience, he is a seasoned professional with a passion for driving impactful research and innovation. He is actively involved in many academic endeavors of the university. So I request to the sir to kindly address the participants. Over to you, sir.
Good evening to all the participants and today's guest, Dr. Durba sir. It is indeed an honor to welcome you to this faculty development program on Geo-AI, innovations in AI for improved spatial data processing. This initiative marks yet another milestone in our journey towards embracing and advancing knowledge in cutting-edge technology. We are living in an era where data is not abundant, but a powerful driver of a change. And educators and researchers, um, it is our responsibility to not only stay abreast of such technologies advancement, but also to impart this knowledge to the next generation of learners. FDPs like this provide us with a platform to do just building a collaborative space where ideas flourish, experiences are shared, and future pathways are charted. I extend my heartfelt gratitude to the organizing team for creating such a relevant and enriching program. I am also immensely grateful to the experts who will be sharing their insights and expertise. To the participants, I encourage you to make the most of this opportunity, engage actively, ask questions, and collaborate with your peers. In conclusion, I'm confident that this FDP will inspire innovative thinking and foster a community of practice that will further the potential of Geo AI in addressing global challenges. So I wish you all the best, and I'm sure that these 5 days will be really fruitful, and the researchers will get a new insight in the applications of geospatial data analysis using AI. So I wish you all the best, and I'm sure that this will be one of the successful FDP organized by Ramravati Institute of Technology, DY Patil deemed to be university. Thank you.
Thank you so much, sir. Now I take the privilege to introduce our chief guest and keynote speaker, Dr. Surya S. Dubal, Professor and Head Center of Studies in Resources Engineering, IIT Bombay, Mumbai. Before joining IIT Bombay, he worked as an assistant research professor at the Center of Advanced Vehicular Systems, Geosystem Research Institute, and also held an adjunct faculty position with the Electrical and Computer Engineering Department at Mississippi State University. Earlier, he worked as a scientist at Indian Institute of Remote Sensing, ISRO, Government of India. He received a PhD degree in computer engineering from Mississippi State University, MS USA, in 2006. At MSU, he researched and developed image information mining tools for content based knowledge retrieval from remote sensing imagery and the retrieval of biophysical variables from multi angle satellite data. He has published over 80 peer-reviewed articles, served on program committees of several international conferences, including SSKI, SSTDM, and so on. He has also co-chaired sessions at various conferences and an invited speaker for HPC, geospatial technologies, and IoT training program in various institutes. He is a manuscript reviewer for IEEE, Elsewhere, Springer, and other high impact journals. He organized the Distributed and Embedded High Performance Computing International Symposium at IIT Bombay in 2016. He received the Excellence in Teaching Award at IIT Bombay and NVIDIA Innovations Award in 2016 for his work in image information, mining, and high performance computing. Also, he received the State Pride Faculty and Outstanding Research Award earlier at MSU. He recently authorized a book on Internet of Things published by Oxford University Press. He is currently an expert member of the National Geospatial Program of DST, member of the Bureau of Indian Standards. He received the prestigious Professor S.P. Sukhtun Excellence in Teaching Award in September 2022. It is a great honor to have such an eminent personality with us. A warm welcome to you, sir. Now, our request to Dr. Surya, sir, for the inaugural address. Over to you, sir.
Okay. First of all, thank you for all those good words. I thank the principal RAIT, the head of the department, Dr. Ekta. Thank Dr. Prakash and the co-coordinator of this course. Thank you for inviting me. I think we are right now at that juncture in the technology development that we are ready to take off. This is the right time, that the time has evolved in such a way that whatever we do now is the one that is going to show the way forward. We are like the torch bearers for tomorrow for this kind of technology to take off, because so many related technologies are now coming together and boiling together to develop this unique area of Geo-AI. And rightly, it has gained a lot of attention. People developing geospatial foundational models, people working on domain adaptation problems, and then application of all these technologies for real world problem solving. Unless it is applied and it is useful for us in some form, technology may be excellent but may not be useful at all. I remember always what Mahatma Gandhi used to say. It seems he said that whenever you are thinking about science or technology, think about the poorest of the poor or those persons who are unadvantaged. Think whether it is going to help them in any way that you are developing. So, for a country like India, it is high time that all of us come together and deliver right now. It's time to deliver some technologies that will percolate into the society for the good of the society. I think Geo AI is positioned in such a way that if we apply in very crucial areas like agriculture, our industrial and applications, and then all those that have a very direct impact on the society. That is what we'll have to think. So I would urge all the researchers present here, when they take up a problem, think how it is going to first impact our country, how we can transform what we are already doing, but in a much better way, and how this excellent technology that is there in our hands is going to foster a new India. So and it is in the hands of all of us. It is not just experts who are going to drive this vehicle. Everybody has a role to play, and with all of us together, we can take this forward. So when we're talking about geospatial AI, we are talking about geospatial sciences by itself. So much has been learned from the past 3-4 decades when GIS has come into play. And then, of course, geospatial understanding has been there for centuries. We cannot deny that. But then the new techniques or the tools that are in our hands have been evolving so much that now we have a geospatial solution for any problem. The other day, someone from our GIS ESRA came to the workshop that I organized recently, and then talking about 18 deep learning models available for 18 different application areas. And if you look at each of that, each one is important. Each one is targeting a very particular application domain. So the first thing I would urge everybody is to develop the domain understanding before jumping into the use of tools or any of these techniques. Domain understanding is most important. If you're working in agriculture, spend time understanding what are the problems, what are the real issues, and how technology can solve. Otherwise, what will happen is that mostly it is data in, data out, something comes out. We don't know what it is. And there is also a danger, because a lot of these tools that are now freely available, in one way it is very good, but the other way is, unless we understand the in and out of using those tools, maybe we are not using it in the right way or in the optimal way. So it is important also to spend time understanding what is happening behind. If it is doing deep learning, it is doing convolution, what is it convolving? What is the output of this convolution layer? What has been extracted? And is it useful to the problem at hand? Is it actually solving what we are looking at? So the easy way is to use 10 networks, try each one of them and try to see what it is giving out, and then proclaim one is working very good. That is the easiest path. The hardest path, but also the best path, is to understand the intricacies of this. For example, I'm just only talking from a deep learning perspective, but applies to other machine learning approaches too. So is the ability to dwell deep into each aspect of that particular technique and see how it can be adapted to the domain of our interest. So this is what I would urge you all, and I am wishing you all a wonderful, fruitful 5 days program. And I'm sure by the end of this 5 days, you will have a lot of new zeal, motivation, and ideas to go back and work on your own problems that will help our country, India. Thank you.
Thank you, sir, for your valuable insights. Now I request Dr. Digambar Puri, sir, co-coordinator of this program, to present the vote of thanks. Over to you, sir.
Thank you, Dr. Ekta ma'am. I would like to thank ATAL AICTE for approving our online FDP. I would also like to thank our Chancellor of the D.Y. Patil deemed to be University, Dr. Vijay Patil sir, and the management, those who have provided the state-of-the-art infrastructure and the labs for the research work. I would also like to thank our motivation and the encouragement of Dr. M.D. Patil sir, the principal of Ramravadik Institute of Technology. I would also like to thank our driving force and the support, Dr. Sangeeta Chaudhary ma'am, head of the Department of Computer Science and Engineering. And I would also like to thank the participants, those who are showing their interest in this area, like Geo-AI, innovations in AI for improving the spatial data processing. And I would also like to thank to all the speakers, those who have given their valuable time to provide their valuable insights in these special areas where now the current trend is going on. And it is a need of the country and the world. So finally, I will wish all the participants to go with some knowledge in this area and try to solve the real world problems in India as well as in the world. Thank you very much.
Thank you, sir. Now I will call Dr. Surya Dubey, sir, to start with the session on Geo-AI in disaster management and emergency response. Over to you, sir.
Okay, thank you. So let me start sharing my screen.
Yes, sir.
So I hope you're able to see it.
Yes, sir. Yes, sir.
Yes, sir.
Your screen.
So this is the one, multi-scale geospatial AI. This slide, are you able to see?
Yes, sir.
Yes, sir.
Okay, great. First of all, I'm on a slow network because I just checked out into a hotel in Goa. I'm attending the Ingaris conference. So I may drop off in between and then I'll again, log in again. If that happens, bear with me. Okay. Because the hotel Wi-Fi doesn't work, so I'm using my own this one. So I will switch off my video just to save the bandwidth.
Okay, sir, no issue.
And then okay. So I have now gone full screen. Are you able to see it? Hello?
No, not yet, sir. I think it's loading.
It's loading. Okay.
Yeah, can you reshare, sir? I think it's
Okay. So it looks to me that I should most probably share the entire screen. That's what it means. So let me do that. Entire screen. Share. I shared the entire screen. Now full screen. Now?
yes, sir. Yes, sir. Yeah.
Yeah, usually that happens with this feature. So, so good evening, everybody. So I'm going to talk a little bit on the multi-skill geospatial AI. So when I talk about scale, scale is one of the important things in geospatial. Whatever we talk about, unless we don't talk about scale, it has no meaning. But then scale, mostly we understand in terms of, we talk about geospatial data, we're talking in terms of spatial resolution. So everybody is interested in having a very high spatial resolution data on which we want to do. But we also have to look at scale that is related to the temporal dimension, the time scale, because geospatial AI is not about simply processing a one date image or processing about one date or one spatial resolution imagery or data sets. It is our ability to seamlessly translate between different spatial scales, temporal scales, the point of view geometry. For example, I'm looking at Nadir all your imagery. Tomorrow I built all these nice models, and somebody gives me an oblique imagery and says, do something with it, you'll have to rebuild all your models. So similarly, if I had a nice models that were built at one time period and then I've got multi-temporal data, your models will not work again. So the fundamental understanding about scale is important. And then the domain that we are capturing at that scale. So a lot has been said and talked about spatial scales, and then everybody wants to look at very high resolution data, and arguably, makes sense. High resolution data will give you a lot more information. But is that really true? Do we need a really high resolution data for everything that we do? So let's see. So what is the time scale we are talking about? Because our time scale could be decadal, it could be years, months, weeks, so on. So for each kind of a time scale, there are particular kinds of domain discourses or domain applications that are pertinent for that particular time scale. So there are changes that can be captured only at a decadal scale, and that makes sense at capturing at a decade scale. So every 10 years, I want to look at see what happens. For example, if I am looking at the ground displacement, the vertical displacement. For example, we all know about Joshimath and what is happening there. So It doesn't change very fast. It's going to change slowly, very slowly. GeoAI is also should be able to capture this kind of very slowly varying geographical phenomenon that is changing. For example, here you can see the vertical displacement of using interferometry SAR to estimate the ground deformation, and then we are looking at very slowly varying time scale 2001 to 2014, 16, 18, right, 2021. So how much time gap are we looking at before the change is actually captured? There are also kind of applications, for example, urban development, groundwater extraction activities. Slowly changing phenomena has to be kept in mind before we jump into use a readily available deep learning model or a machine learning model that is available to run on it. So land subsidence, surface faulting, hazard, and risk assessment, all these are all decadal in nature. We're also looking at decadal land use. Half a decade usually is what Forest Survey of India looks at when they're looking at forest cover change, forest maps that they're looking at. They're not looking at what is happening every month. It is not a good way to look at it. So this kind of time frame has to be understood. Now, what is the data I need? How much is the data should I need? What is the number of years of data should I take an average of this data, or it should be median? What is it? How do I condition this data to address this kind of problem? So the everything in GeoAI is all about first understanding what is the data that you need and how do you condition that data to solve the particular problem. So if this is understood properly, the rest is only tweaking few things. But then this understanding is possible only if the domain is understood properly. So, and then we are talking now about multiple years changes that are happening over a period of time, say 2014, 2004 to 2016, how in a particular area has transformed. If you're talking about Mumbai also had a lot of changes happening. A lot of suburbs have grown over multiple years, and there is urban sprawl. But then understanding what is the direction of this urban sprawl versus one area, one side it is growing more while the other side is stagnant. What are the reasons? That is the intelligence. So the intelligence has to be given by the application, by the tool that you are developing. Why particular sides of Mumbai is growing more? What is the reason? Simply saying that okay, on the northern side of Mumbai it has changed a lot in last 10 years doesn't make, it makes sense, but it is not too much useful. Maybe you'll add few more layers on top of it and say okay, there are more industries coming, it is going there. But is that really intelligence? So we will have to look at many more ways to understand this kind of a change. What is the reason? And then here we're talking about from a yearly to a monthly time scale. Here you can see the NDVI monthly from January to December, how it is changing over 2 or 3 crop cycles. That is happening. So there is definitely an understanding that you can gain when you look at the monthly changes that are happening. But as you will see that most of the time when NDVI data is used, I've seen a lot of people simply using the NDVI of one date and the NDVI for other date, or NDVI, a very closely spaced NDVI data sets being used in the research. It doesn't make sense, isn't it? That's the reason why, if you look at the data that is given by some of these agencies, for example, Moody's or the Sentinel or any of these things, they will give you a composite of the data, NDVI composite, because it is, well, I don't understand. They'll say it's like 6-day composite or 7-day composite or 16 days composite, something like that. Because it is understood that if you are looking at that kind of time frame on an NDVI, the changes that it is depicting from one composite to the other makes sense. Because you may not be able to see anything if you're looking at NDVI today and tomorrow. Not much change. It's not going to give. So there is a specified temporal window in which you need to look at this particular phenomenon. So if this data is not done in that way, it doesn't matter what kind of deep learning or machine learning algorithms they use, the ultimate analysis will not reflect the actual changes if you are trying to track the phenology of a crop. It's important to understand this. The composite, what is the, how many days composite should be used? And here we are using mean monthly NDVI. So it means that if you're tracking over a 1 year, monthly mean NDVI is enough to track what is happening to this either forest or an agriculture area, or over a 1 year period, what happened, what changed to what is happening. It is, although I may get data every day, we should not use it. Not useful. There may be certain applications for it you may have to look at, but not for all of them. So what is the take-home message is that it is important to understand a phenomena and how that phenomena is behaving in space. That is geospatial. Here we are talking about weekly, a phenomena that is tracked in a weekly cycle. We're talking, for example, turbidity or some variation.
Sir, you are on mute.
Sir, you went to mute.
Suddenly,
Sir, you are not audible.
about now,
Yes, sir. Probably you can mute your video, sir, and then share the screen.
Can you hear me now?
Yes, sir.
Yes,
We can hear you now.
yes,
Yeah.
sir.
Yes, sir, you are audible.
So I don't know till what time you have seen heard me. Next
Okay.
time stop me immediately.
Yes, sir. Maybe you can mute your video, sir. That will be better.
Video I did. Video I stopped.
Yes, sir. Yes, sir. Yeah.
I shared something you're able to see or not.
We are seeing the entire screen.
You're seeing the entire screen. Good. Good.
Eh, I mean, it's still loading, I think.
Yeah.
Yeah, yes, sir. Now
Yes,
we
now
can
visible.
see.
Yes, sir, yes.
Give it. So you heard this weekly thing that I talked about?
No, only half of it, sir.
Only half of it.
Yeah.
Monthly thing you have heard about
Yeah.
it?
Yes. Yes.
Yes,
Yes.
monthly Goya.
So for weekly, we are talking about a phenomena like capturing the turbidity of a water body, like our Powai Lake in IT Bombay, which is polluted. Uh, so we've been doing a lot of work trying to see pre-post monsoon how the turbidity levels are, the pH is, but we'll have to track it at a different time scale in a weekly kind of a thing. So there is a chance that it's going to change. So there's another phenomena like the harmful algal blooms. So these harmful algal blooms are like algae that spread on the ocean for a large distance in kilometers, and then it is going to take up the oxygen from the water, and ultimately the fish below it die, and then you have this fish that are washed onto the shore. So this is a phenomena that works at weekly time scales, phenomena that spreads slowly over the ocean, a phenomena that is so large that you don't need a high resolution data set. An AVHR data set like 7-8 kilometers per pixel is enough to track such a kind of a phenomenon. So now we're talking about a spatial scale, a spatial resolution that is very large because the phenomena itself is that way. There is no point in tracking this every 100 meters or every 10 meters using Sentinel, for example. So this is a spatial and then temporal evolution of this phenomena. How do you take this spatial time series data to do this? So earlier we did some work related to this harmful algal blooms in the coast of Florida, and we tracked several parameters related to the algal blooms that capture its unique characteristics. So this is a spatial temporal variability of 30 days. So we can see that it is increasing from day 1 to day 30. And then we are able to look at a three-dimensional representation, latitude, longitude, and time over how it is changing to be able to understand this one. So what I'm trying to get is that the temporal time scale makes a lot of difference in the way you analyze your geospatial data. So the GeoAI models definitely have to capture the temporal dimension before you can say that it's a generalized model that can be applied in various situations. Here is an example of a daily monitoring where geospatial AI approaches can be used for forest fire monitoring. But then this is a monitoring at a very coarse scale. Modis, for example, gives a fire pixel. It's available every day. It will give in various parts of the world. These are fire pixels captured from the thermal camera. So it is going to show you what it is, just tells you about the temperature and then its own model of saying there is a forest fire. It may not be accurate and it's not been validated at many places also. So, and then here is an example of a daily evapotranspiration at field scale, which is obtained by multiple satellite data fusion. Now, here is another problem when we're talking about geospatial AI is that one satellite data at one spatial scale or at one temporal scale or the revisit that it does may not suffice our requirements. And the easy way out is simply to take it at one spatial scale, just make it coarser or finer by interpolation or doing other kinds of transformations, which is not correct, which is will give you a lot of erroneous details. I've got one very nice data set at Landsat, but some other data set is at Moody's 250 meters resolution. What to do now is a problem that we grapple with. And then I've got this another data set that is in situ data set. Now, how do I combine that data set with the other Landsat and Moody's and bring them all together so that I get this nice fusion data set? So image fusion is also an important problem. And then all these are coming at different time scales. They've got different radiometric properties, calibrations are very different. So care has to be taken to be able to resolve all these problems before the data set is deemed to be ready for the next level of processing. So the very first thing is understand scale, both spatial and temporal. If necessary, data fusion is required to be able to combine them, and then use that data set for your other downstream tasks that you are looking at. So here is an example of hourly ozone prediction. Now we are talking in terms of hours, and this data set could come from your air quality monitoring stations, hourly ozone data or particulate matter 2.5 microns or 10 microns. All this is also all geospatial in nature. If you put or have put all this air quality monitoring station in Delhi, each monitoring station has got a geospatial location, and then there's a network of them. Now it's a geospatial problem, how the pollution is happening, and then you're tracking at particular times of the day, which is important. I will just take it in this morning at 7 o'clock and say this is what is the spread. It doesn't make sense. So you need to have hourly predictions. Now the geospatial model has to be changed. And then now this is a data that is coming in the streaming fashion. This is not your regular data that you have got a snapshot and then in the archive you pulled it up and working your model. This is streaming data. So streaming geospatial data. So the models are entirely different from your normal machine learning models. So that is a new area has evolved. Well, the stream data mining approaches. Your normal, decision trees won't work. You have to use a Huffington tree because the model that you have built in the last 2-3 hours of this data that you used may not work in the next hour because that whatever you're tracking may have changed, slowly drifted away into a new distribution, into a new statistical distribution. This is called as concept drift. So capturing the concept drift is very important and using that drift to again refine your models so that continuously you are adapting to the changing conditions. This is geospatial AI problem. When you're working with geospatial data that is streaming in fashion today, IoT data, geospatial IoT data, a lot of this is a streaming, streaming clustering, streaming classification. The models are very different. You cannot build a static model like the classical models. Either you build with machine learning or with deep learning, doesn't matter. None of this model will work for this kind of data. So this is another thing we need to keep in mind. What is that data we are using? So people, I have seen that many are using streaming data but building one snapshot models, which is not useful in reality. And here is a very good example of what Ola, Uber, and all of these people, Swiggy, everybody wants to estimation intersection delays from whatever is the traffic. Half an hour I'll deliver you the pizza, otherwise it is free. Means there is a model behind. They will want to make an estimation, saying what would be otherwise. If they find it within half an hour, it is not there, they'll have to reroute. Immediately reroute all these things based upon these things. So already, companies are using this kind of models to be able to change their predictive models or adapt their predictive models based upon the data that is coming in. So this kind of understanding will help you to think about, move away from the simple static models that we have been doing for many, many years now, to a more dynamic, adaptive kind of models. And all this is geospatial in nature. So one of the fundamental things to keep in mind is that any algorithm that we are using, doesn't matter any deep learning networks that are available or any machine learning models, in your data set, are you specifically using any geospatial data in that model? If you are not using it, it means that you have fundamentally not used the inherent geospatial geospatial phenomena is not being captured in that model. If you don't do that, what will happen, we will see in a minute. So how do we formalize the problem? So you got an hypothesis. So we are thinking something, okay, X is related to Y. Is what we want to say the hypothesis is, we want to think about. Finally, you want to develop this hypothesis based upon your understanding. So for normal models, if they're not in streaming fashion, normal models, X and Y have to be labeled data. For streaming data, X and Y even it could be labeled data, but then this your Y could change because the concept may drift over a period of time. So these classical models will not work. We can just throw them away. So when we are trying to do this, we want to find such that potential candidate model we have, but there could be many potential candidate models. Out of that potential candidate models, we want to select one. So find a function of input attributes best predicts the outcome of your output variables. So this is what we're interested in. There could be many potential models that may work, but they're not useful for us. So hypothesis is basically you're talking about a data and you got some algorithm and then you got a function that we are trying to work. So ultimately we are trying to create a function that best explains the whatever is the hypothesis that we are looking at. But then if you look at this one, these days when you're talking about deep learning, we don't know what this function is. It's like a kind of black box. I don't know what it did. But there are ways for a normal machine learning model, for example, SVM or any other models, you can actually derive a function telling what is the function. It is this thing. For example, I can use the logistic or Platt's logistic formulation to use the SVM to create a function actually to understand what it is. So like that, it is important. So sometimes, most of the times, we lack this kind of understanding of this function. So we don't know what is happening. So this has to be kept in mind. So basically, our motivation is extraction of thematic maps from satellite images. So input Landsat image, you get an output classified image. So Prakash, how much time do I have?
Sir, till 8 o'clock, sir.
8 o'clock. Okay. Till 8 o'clock. Okay, fine. So, okay. So
I
here,
mean, sorry, the last 15-20 minutes will be for Q&A session. Yeah.
okay. Okay.
So,
So
yes.
7:30, I'll try to finish.
Yeah,
Okay.
7:30, 7:40, you can finish.
Okay. Fine. So our motivation is basically to take a input image and then create a classified output image. So we extract these images, forest fires, floods, earthquakes. Many of these things is possible. So our image classification has been around for many days. You take some samples, like in the top image, all the squares, or you take some samples of water, take some sample of urban areas, or any of this, forests, agriculture. And then you also take them in different bands: blue, green, red, infrared, whatever, thermal. And then you have a corresponding output. So basically, what we are trying to do is we fit y is equal to fx plus some with some noise or error that we are at. So this is a very classical maximum likelihood approach, where we use the Bayes theorem to compute a label, whether x belongs to a particular label or not. Right? So a pixel, we want to look at a pixel and say, does this pixel belong to this class or not? What is happening? Pixel from any class at a location X. Each pixel, whatever. Finally, that is what we are trying to look at in a maximum like. But then we find that by using these things, you have a lot of data is required to do such a kind of models. And there is a requirement for training data. Of course, these days we are also looking at reinforcement learning, deep reinforcement learning, for example, where you don't need to add a training data at all. Very interesting problems are being done in that area now. And then we have supervised learning techniques, many of these things. I have not put deep learning purposefully here because unless you understand machine learning in a proper way, getting the deep learning is not a good thing. You have to start from the very basic, understand what is naive-Bayes classifier, for example. So it is important to do this. So once, because what we are looking at is generative kind of models, for example, that which are based upon your probability theory, your maximum likelihood classifier. Basically, they're learning joint probability. But if you also have a discriminative models where it is actually learning the conditional probability, and it's trying to find a hyperplane, for example, a maximum margin hyperplane, for example. So as we continue this, and you will see that there are so much of work that has already been done. So in this lecture, I will touch upon a few of these things. For example, in this cloud of these words, you can see a transfer, you can see adaptation, and SVM, you do learning. So we will see how some of these are very important for Geo-AI and how we will be able to solve no, real world problems. So the geospatial everything begins with a sample, a random variable. But then there is a particular characteristics for the sample, saying that the sample is independent and identically distributed with the other samples. Then only that sample is. So if they're not independent, then the samples are actually related with each other. So our fundamental statistical. So it means that we will now have to deal with the data that is related with each other, that is not independent and identically distributed, but it is identical. It's not independent with the next sample. So this is a problem of spatial data. Once we thoroughly understand this problem in terms of what is called as spatial autocorrelation, if spatial autocorrelation is understood properly, then we will realize that whatever be the machine learning algorithm that we are using on spatial data may not give us optimal results. They'll give something, some result it will come, but that is not the optimal result. But if I realize that they are not IID, independent identically distributed, but they are actually spatially correlated, and I have a way to quantify this spatial autocorrelation by looking at the neighborhood of this sample that we are looking at. And there are many ways to look at the neighborhood and then quantify the neighborhood and understand whether this neighborhood, these samples are clustered or they are dispersed totally, or these samples are in between clustering and dispersion, and I will be able to do something. And if I use that knowledge to be able to use in my machine learning or deep learning models, then it makes sense. Then it means that truly you have used the spatial phenomena. And then also, like I mentioned earlier, now that is the true problem. That is the true approach to. So if test distribution is different, so a lot of times we on some training data, but then when I look at the and try to apply it on a real world situation that is maybe slightly different work. This is regression model. Be very careful. Make sure every condition that you have used as a it is there, it will not work. So that is a problem. So it is not possible for me to collect this exhaustive kind of conditions in which this data data sets can be captured. So if that is not the case, when we think as a humans, if we think about it, in your uh, or it looks like agriculture, it is not actually agriculture, it is a plantation. I will make that difference. I will be able to do that because I transferred some knowledge. Make this transfer of when we are with a lot of situations, many situations where we will not have true no, true or same or real world. So a lot of times we get confused. The model, but there will be an issue. Just hold. Okay. Just hold on a minute.
Hello, sir, are you there?
Dear participants, speaker sir will join in 5 minutes due to network issue. They have some problem, so have patience.
Can you hear
Yes,
me?
yes,
Hello,
yes.
can you hear me?
Yeah,
Okay, okay. So I
yeah,
lost
yeah.
power in between in the hotel. I don't know what.
No problems.
Okay, bear with
Yes,
me.
no, don't worry. Yeah, please share your screen, sir. Yeah.
Yes, I just shared it. Are you able to see it?
Yes, yes, sir. Yeah.
Oh, okay. So we are talking about now about small samples. when you're talking about maximum likelihood classification or even for the regression kind of models, we usually say get as much data as you can, but it doesn't mean that you get data that is got less variability. The idea is that capture as much variability of the phenomena that you can, and is possible for you. It means that capture the lows, highs, mediums, and then any other thing that is there in that phenomena. That is the kind of sample that and the more you get of these things, the more variety that is being captured in your samples, the better it is for you to build the models. So if you have a labeled plus unlabeled data set and you've got a lot of data, you can see the accuracy has jumped to 64, for example. Then data, if you're just using only the small amount of labeled data. So insight is you need large number of labeled samples. This is how deep learning is working on. It needs so much of data. Unless you feed large amount of data, deep learning will not work with small data sets. But earlier we did, right? We were able to build these nice, beautiful models, for example, using SVM, which can work on sparse data sets. Now, we have this limitation of deep learning that you need, unless you got a lot of data, it cannot do. Then we now resort to other ways of generating data, generative networks, for example. So everything, each one has got its own ups and downs. But we will see here that when we want to work with a small sample size, as I will show you in a real world application where you have only small number of labeled samples. I'll show you only for one area, but it is the case for many real world cases where actually you don't have a lot of data. Especially if you're looking at healthcare, for example. There are not too many labeled samples for a particular specialized area that you're working with. You can't get them. So inaccessible areas, for example, you can't get a lot of these data sets. So the way to do this, you reduce the number of parameters to be reduced, do the dimensional reduction, and use all kinds of semi-supervised approaches. But one attractive way to do is the domain adaptation. So, okay, we'll come back to this one. So the transfer learning is about a sequential process where you're trying to reuse whatever knowledge that you have. And then you are going to look at how to use it to a different task that you're looking at. So to that ex- actually the way our human brain also. do this all the time. We keep on transferring what we have learned.
Hello.
Okay. Okay, I rejoined. I hope you are able to see my screen. Can you see the screen?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
So,
Yes, sir.
so the traditional machine learning versus transfer learning is we are trying to transfer learning across different domains, is what we. So, for example, I know about something about airplanes, right? Some tracker of aircrafts. If I know a few things about the aircraft related to the wings or the nose or something, I can transfer it and then be able to capture a whole host of airplanes that may be of slightly different nature, or their shapes may be slightly different, but there are certain characteristics that I've captured. That is called as prior knowledge. Capturing the prior knowledge is very important to do this. So many areas, this kind of transfer learning people have been using frequent words or song genre predictions or handwritten letters. So there is there is a evolution of this kind of approaches starting in 2006, where I published my first paper around 2011. Work has started, and based and generative network based
Dear participants, the speaker will rejoin in 2 minutes.
Yeah, sorry, I just joined on the mobile. I think we can conclude. I can take a few questions because network is very spotty here.
Okay, no issue, sir. Thank you so much, sir, for sharing the valuable insight with us. Now it's time for us to engage in the question and answer sessions. So this is your chance to ask any questions you have regarding the topic discussed. So please free to all participants to ask the question and answer session.
Hello, sir. Good
Yes,
evening.
yes.
Sir Chandan this side.
Hmm.
Sir, I have one question on temperature modeling, sir. When
Okay,
we speak about the climate change, I think one or two slides you just touched on that part also.
right.
So when we speak about the temperature, sir, in the climate change context, sir, what are the basic layers, geospatial layers that you suggest us to take for the modeling, sir, for the
Yeah.
temperature modeling?
See, usually temperatures and all these things from a climate perspective, they are all run models called the general circulation models,
Yes, sir.
GCMs,
Yes,
right?
sir.
So the GCMs usually work at a very coarse resolution, like half a degree by half a degree or quarter degree by quarter degree. That is the kind of spatial resolution on which they work. So your data sets usually have to be related to that resolution. But usually one uh, layer that is common to is the land use land cover layer that
Okay.
you will have to use it. Example. So layers also related to your understanding of your what is called as gross primary productivity, net primary productivity, NPP. All these are all derived using satellite data. So you have to look at these layers, and also you have to understand what is the land surface temperature, sea surface temperature, SST, all derived from satellite data. Okay. Uh, yeah, and then the other important thing is that you will also have to think about very large time scale when we are talking about temperature and all these things. So climate change is usually something they talk about like 25 years, statistically speaking. It is not that it didn't rain in Mumbai last monsoon. There is because of climate change we cannot declare it. It could be of some micro climatic process or very local processes that are doing that. So, and then there are some of the things that are cyclical in nature. For example, your El Nino, La Nina effects, all these things. So it is important to consider both large time frame and large spatial scale to be able to come to some conclusion related to the climate change variables. Okay?
Understood, sir. Thank you, sir.
Yes, sure.
So one more question.
Hmm.
Could Geo AI tools be employed to track environmental factors or urban infrastructure that contribute to any disease in certain regions?
Yeah. So disease tracking is a very big area. Geospatial health GIS is a very big area, sub area of GIS. So what they do is to understand, it's called as they will track the vector-borne diseases, diseases that can be tracked, their movement along a particular direction. So our government is very interested, Center for Disease Control, and all of them are interested to see, one is how the disease is moving in a particular direction, and the second is what are these clusters of this disease and their intensity that has. So geospatial AI, just like I mentioned about, now this is a spatio-temporal problem. Whatever we have discussed, both in spatial and temporal scale, first need to be understood is that how this disease spreads, how much time it takes, what is the incubation period of this disease before it actually shows up, and what are those vulnerable areas where this disease may become severe? What are the environmental conditions that are conducive? For example, some of the disease may be conducive based upon the temperature, humidity, or any other related environmental factors that will make the disease be able to make it severe. There are a lot of studies, earlier and during COVID time also relating air pollution to COVID severity. There are certain indicative research that said that areas having air pollution, there was also some disease related intensity has increased. So those are all mostly is a geospatial kind of a problem. Okay.
Okay, so like if I wish to do risk profiling or something likewise.
Basically, what first thing you have to do is, because risk profile you are talking is related to humans in the loop. You're not just talking about disease, but you're relating it to the humans. Now, you will have to what do is basically build an index, a vulnerability index. I would suggest to get you started is first look at the United Nations UN indices are there. There are many indices. United Nations have developed, and they have shown particularly how to develop these indices. We have done one such work. One of MTech students did it. I can pass on that thesis to you, where we developed indices specifically for the COVID, using some of the United Nations indices as our base. Okay. So that index should incorporate both spatial variables as well as the disease-specific variables. So disease-specific variables, for example, is like a model that we have used to tell the intensity. That is a model. So the model related to the disease-specific variables, and then variables related to the human, that is related to your socioeconomic indicators, your income levels, your population, all these related aspects have to be integrated into that index to be able to say something about it. Okay.
Okay, one more question is there, sir. How can we capture and handle the concept drift in geospatial data?
Concept drift. Okay.
Yes, sir.
Yeah. So concept drift, this is a current ongoing work at CSR. We are doing it. So concept drift can be captured by so many, and there are so many methods that are there, but specifically you will have to look at stream mining approaches. So concept drift happens in such a way that usually it is not noticeable. Concept drift happens very, very slowly. So drift in concept, what I mean is that, I'll give a simple example. So if you are capturing something on your UAV or a drone, you've got a multispectral camera, and you're capturing a terrain. And then you're thinking, okay, I'm capturing this image, why don't I just classify it? I have these models to classify if it's a vegetation, it is something. But what happens is, as it is capturing, there is a concept, the plain area with vegetation, forest area, agriculture area, grassland, slowly it is changing into a different terrain. And again it picks up into a different terrain, right? So what happened? My original concept of vegetation has now gradually changed into a different concept called the drift. So this drift has to be statistically modeled, or you can also capture this drift using machine learning models. So it is a function of space and time. Both has to be captured into account. So once you capture this drift, you say that, okay, now the model I'm running for vegetation, there's a drift has happened. Now I should not run this vegetation model, but I have to run a different model to be able to classify it, or change this model accordingly based upon the drift. Again, we'll have to also capture whether it's a serious drift, means a large drift has happened, medium drift has happened, low drift has happened. What is your threshold of tolerance of this drift? So it's a very big area. I would suggest you to you email me. I will point you to the resources.
Okay, sure, sir. Okay. Yes, anyone else participants? Any questions from your side? Okay. Thank you, sir. We are done with the question and answer sessions.
Okay.
Now it's time to express our sincere thanks to your eminent expert, Dr. Surya sir, for his insightful presentations on Geo-AI in disaster management and emergency response. We request you to accept this virtual memento as a token of appreciation and gratitude, sir.
Thank you. Really appreciate it.
Sir, we are truly grateful for your time and expertise that you shared with us. Your sessions has given us a lot to think about various aspects for spatial temporal data mining approach for harmful algal blooms detection and applications of Geo AI in disaster management and emergency response. Thank you so much, sir. Now
Great.
here I am. One announcement is that all are requested to fill the attendance as well as the feedback link is shared in the chat. Thank you,
Okay.
everyone.
Okay.
Thank you so
Thank
much,
you all.
sir,
I
for
will
your
log off. Okay.
yeah. Thank you
Bye
so
bye.
much, sir.
Yeah, thank you so much, sir. Thank you so much for the insightful session and sparing a time for taking a session.
Yeah, most welcome. I wish I had a better network, but next time. Okay. All the best.
Yeah, thank you so
Yeah.
much, sir.
Bye bye.
Thank you, sir.
Bye.
Dear participants, we will take a short break on 5 minutes. After that, we resume the session.
I think a participant has raised the hand. You can unmute yourself and put forward if you are having any query. Varsha. Okay.
Varsha ma'am, you want to say something?
Hello.
Yes, ma'am.
Yes, ma'am. Go ahead.
Okay.
Umesh sir. Umesh sir, are you there?
I think he didn't join yet. He will join.
Yeah, ma'am.
Yes.
He has joined.
He has joined?
Yeah.
I could not see.
Sir has joined and left. He thought the other lecture is going on. Yeah.
Okay, then he may join
Yeah,
in
yeah,
same time.
yeah, yeah. I have called. He's joining.
Okay.
No, sir.
Uh,
Yes, sir.
Hello.
Yes, sir. You can
Yeah, sir,
share
you
your.
are audible.
Yeah, you are audible.
Yeah, I'll just share my screen just to make sure that.
Yes, sir.
Yes.
Is this visible?
No, sir.
Yeah, yeah.
Yeah,
Yes, sir.
yeah, it's visible.
Okay, and
Yeah.
let me do full screen. Is the full screen view visible?
Yeah, sir.
Yeah, yes.
Okay. It's a presentation.
Perfect, perfect, perfect. Yeah.
So we'll wait for 2 minutes, sir, and then we'll start.
Yeah, sure, sure. No problem. I'm just joining
Yeah.
from my mobile because this Wi-Fi, hotel Wi-Fi that I'm staying at just did not give good bandwidth. So that's why I'm
Yeah,
keeping my
no
video on.
problem, sir. Yeah, yeah, yeah.
Yeah,
Thank
By
you.
no
keeping a
issue.
video off, it will be better to have a clear audio signal.
Yeah,
Yes.
thanks.
Ma'am, can we start?
Hello?
Yes, ma'am. Can we start the
Yeah,
second
we can
session?
start. Yeah. Hello, Dr.
Yeah.
Unmesh. Hello?
Hello, hi.
Yeah, Sangeeta here.
Hello, ma'am.
Yeah, hi.
Hello,
So,
hi.
Yeah, we can start, Ekta ma'am.
yeah, ma'am. Thank you, ma'am. So,
Yeah,
welcome back. Now we are moving towards a next session on our event on scalable computations for geospatial data. So, we are delighted to have with us today Dr. Anmesh Khati, a rising star in the field of remote sensing and Earth observation, who will enlighten us with his expertise and groundbreaking research. Dr. Kanti sir is an assistant professor in the Department of Astronomy, Astrophysics, and Space Engineering at IIT Indore, where he leads the cutting edge remote sensing lab. A distinguished alumnus of IIT Bombay, Dr. Umesh Kanti earned his PhD in radar remote sensing in 2019. Following his doctoral studies, he furthered his research as a postdoctoral fellow at NASA Jet Propulsion Laboratory at the California Institute of Technology. During his time at JPL, Dr. Sir contributes significantly to the prestigious NASA ISRO synthetic aperture radar mission, a landmark collaboration between the United States and India. He has more than 12 years of teaching and research experience. His current research focuses on utilizing remote sensing data from satellites and UAV platforms for critical applications, including ecosystem monitoring, carbon tracking, sustainable city planning, and advancement in forestry and agriculture. So today's Dr. Unmesh Khatib share his insight on scalable computations for geospatial data. So providing a deeper understanding of how remote sensing technologies are shaping a sustainable future. So welcome us to join the sir. Over to you, sir, to start the session.
thank you. Thank you so much for a very kind introduction. And Unmesh is correct
Yeah.
pronunciation. So
Sorry,
thanks
sir,
for that.
for that.
No problem. Thank you. Welcome all to this second session. And before we go into a little bit about scalable computations, I would like to just give a gist about what I am doing, as well as what my role has been with respect to scalable geocomputations. So, as already has been kindly introduced, I did my PhD from IIT Bombay and subsequently was a postdoc at JPL. So during my time at JPL, as well as earlier stints during my Fulbright fellowship during my PhD, I have been associated with this map platform, and I will discuss a bit about this at the end as a demonstration of how we are using map as a geocomputational platform to generate global data sets. So I have created a recorded session with my colleague Marco from NASA. Both of us work on this particular project, have worked. And so this is a joint project between NASA and the European Space Agency, and MAP stands for Multi-Mission Algorithm and Analysis Platform. So this is one of the initial stages of the project. So currently it's in the beta version, and one of the things that I have been doing with it is I have been a algorithm developer as well as tester on this, especially for the NISAR mission. So we will come to that, what it is and how we use it. A little bit about the work that we do. So I lead the remote sensing group and lab at IIT Indore, and we work a lot nowadays with drones. We have a bunch of hyperspectral, multispectral, as well as thermal remote sensing instruments which fly on our drones, and we do a lot of ground-based instrumentation, as well as DIY labs and sensor breakouts with our UG students. And for the group that I lead, the research group, it's the radar remote sensing group, and uh, the we mostly concentrate on ecosystem studies, such as deforestation mapping, biomass estimations, height estimations of the forest, as well as do some sort of a 3D structure retrieval using GeoAI as well as tomography data. In the center, you can see some of the work that we have done for disaster monitoring and mapping for the Kerala landslides in 2024, as well as earlier the heavy rainfall events which led to inundations during the 2018 floods. On the bottom, you can see the cropland data layers that we extract and map using the simulated NISAR datasets. And on the right-hand side is what we are interested in for this session, which is global mapping of a parameter. So here, the example that we'll discuss more in detail will be about the global forest biomass or global forest carbon mapping. So what I have done is, since this is at the initial stages of this entire discussion, I have chosen to start from a little basics. So I am hoping that most of you know about remote sensing, but still, in the interest of a larger audience, I have kept a few slides on what is basic remote sensing, not very basic physics of remote sensing, but just what is an overview of remote sensing. And then we will dig a little deeper into three specific areas where nowadays the amount of data that is coming in and potentially in future is huge, which will be in terabytes per day. And so these are hyperspectral, LiDAR, and radar. So these three are the big data producers in remote sensing. So we'll go a little deeper into each of these. Then we will understand, once we know what we are dealing with, then the question should comes that what is the need for scalable computations in geospatial data? Why are we now not uh, uh, why is not a simple server or a workstation enough to process the geospatial data? And then I'll go into specific examples. So the example that I'll give a little bit about xarrays, which can be used by any person with Python experience, and then map, which is this platform that we work on. So under remote sensing, the question why use remote sensing is, I think, probably answered for you through the previous talk on disasters, as well as you might have a basic knowledge. So a very brief gist is that whenever we want to have a synoptic coverage, which means that a coverage over a very large area, we want a sensor which will be able to map that area and get us some sort of insights. So only capturing photographs is no longer enough. We need to understand what is happening. And so on that photograph, you apply an analysis technique. That's where the remote sensing part comes in. I'll quickly give an overview of what are the types of sensors and the data. And although I'll not cover here what is the off-shelf data, but typically for forest inventories, the one particular application, we do use some off-shelf data. So that part we'll not cover in this. So when we deal, let's say, just with the ecosystems, we can go and use a simple optical RGB camera. So I can mount that on a drone, or I can mount that on a satellite, and it can give me information such as forest mapping, forest change. So I've intentionally kept one application only in this talk, because if I start talking about all the applications, it might get a little confusing of what is the advantage of one technique or one particular sensor over the other. So let's suppose you want to only map the forest and its change, whether there is a forest today and the forest was, let's say, cut off in a couple of months. So just that change, an optical RGB camera would be sufficient to give. The moment we want some sort of a biochemical properties, which means that I want to know what is the chlorophyll content of that forest, or a vegetated area, or some sort of a, let's say, leaf area index, so which are again related to the amount of productivity. I want something which is multispectral, which means that I'm also interested to understand what is the reflectance of that particular target not only in the red, green, and blue, but also in the near infrared sensors. If I want to have much more information about the biochemical properties at a much finer resolution, I would go for a hyperspectral sensor. So with hyperspectral, you might go all the way up to yield estimates. You might go all the way up to detecting pest at an early stage, as well as detecting disease, water stress, and go to some sort of a smart agriculture or a precision agriculture. When we want to come to some sort of a structural estimations, there are two techniques. So if I want to only map, let's say, height of a target.
Sir, you are not audible.
He's rejoining, I think. So
I think I got lost. Is this visible?
Yes, sir.
Yes.
Yes.
Yeah. So was I audible up to this point, or did I miss a couple of slides?
We were on this slide, sir.
Okay. Okay. So hopefully I covered up to LiDAR before I dropped off. And so just to recap, LiDAR sensors essentially will provide more information about the kind of a target that the target height and structure that we want. When we want to go to a sensor which is not sensitive to the cloud cover. So if I want to map an area irrespective of the cloud cover and irrespective of the weather conditions, then I would like to go for a synthetic aperture radar. So this is sensitive to the biophysical properties such as the volume, stock volume, or so as to say the amount of wood that is there in a forest, the biomass, carbon content, the changes in the forest. And so these parameters, irrespective of the presence or absence of a cloud, will be mapped using SAR, which will not be possible for a LiDAR or a hyperspectral sensor to do, since they have the reflectance from the cloud, which will block the any kind of a radiation that is getting reflected off in that particular wavelength for hyperspectral or LiDAR. Now, when we have this platform, we can mount it on a ground-based sensor, ground-based platform such as a UAV, and it can fly a few hundred meters. If you want to capture over a wider area, then a airborne platform such as some sort of a aircraft or at least a helicopter will do to do aerial photography or photogrammetry or any sort of other sensor. But typically, most of us have been using the spaceborne data. So spaceborne data in the earlier avatar were coming from the special space shuttle. So we had a host of instruments on the space shuttle. One of the earliest remote sensing, radar remote sensing, especially instruments came from the SIR, the shuttle imaging radar, and which had both an optical and a radar sensor on top of on the same platform. And then we had a lot of now there are a lot of space-borne constellations from all the major space agencies. So ISRO also has a host of optical and SAR constellations. NASA has ESA and JAXA has, and so on and so forth. So it can provide us with all sorts of products related to the targets that are of interest for us on the ground, as well as a lot of applications. The sensors typically either use the sunlight as the source of energy, and so these are called as passive sensors. They are measuring only the reflectance of the target, and so they are sensitive to the photochemical properties of the target, and so the color variations as well as the spectral variations, those are the important parameters to study in case of passive sensors. And a knowledge of the radiative transfer theory is also a very good idea to use when we are dealing with passive sensors. When we want to have our own source of energy, we move to active sensors. These are the sensors that are transmitting their own electromagnetic radiation and receiving back the return. These can be LiDAR sensors, or these can also be radar sensors. Both of them have their different distinct advantages with respect to the passive sensors. Now, coming to platforms, so we have been using platforms on uh, uh, and can have simple cameras mounted or specialized instruments such as hyperspectral sensor. You can also mount, let's say, a methane detector on the platform, and it's still a remote sensing sensor, although it is not an imaging sensor, and it will go on detecting the methane as the drone flies. We also have platforms like satellites and microsatellites, which can host a constellation of these data. Now, let's dig a little deeper into each of these sensors, hyperspectral, then LiDAR, and then radar, and see that what they measure and then why so much amount of data is now coming in, which requires us to have something like a scalable geocomputations. So let's look at a few example applications with these three, which provide a lot of big geospatial data. So first, I will go into hyperspectral sensing. So hyperspectral, as the name suggests, it basically is a scanner which has a lot of detectors, wherein the detectors are sensitive to different wavelengths. And we really basically have a very high spectral resolution with respect to a multispectral sensor. So the image on the right here on the x-axis is the wavelength, which goes from zero point 0.4, which is just the edge of UV spectrum, all the way up to 2.6, which is a very far infrared spectra. On the y-axis, you have the reflectance, which is shown in percentage of the received radiation. So it is basically the ratio of reflectance divided by the irradiance. What these three curves show is the one in the dashed line shows a water, the reflectance of water. So as we can see, the water reflects little bit as a total percentage. It's only at max 8 to 10% of the total radiation that it receives, it reflects. And most of this reflection happens in the and most of this radiation reflectance happens in the blue-green spectra. So that's why water sometimes looks little bit bluish green, and then very less radiation is there in the red spectra. It's very minute, and then almost there is nothing once we go into the near infrared. So it basically shows that water is absorbing a lot of this near infrared radiation. And always like physics, we something which is absorbing something is basically going to absorb that energy also. And so water has a very high specific heat capacity, and this much amount of energy it absorbs. And that's why we have the specific mass and specific heat capacity, which basically also controls a lot of the Earth's atmosphere, Earth's weather parameters. Now let's go to the solid line. The solid line shows the vegetation. Now, if we had this solid line, which is the spectroradiometer reflectance curve, we can see that in the green spectra around 0.5, it has a peak. And after 0 0.6, 0 0.65, 0 0.7, we cannot see anything. And so in the visible spectra, the visible light to us, the vegetation appears green to us. While if we were to observe it in the near infrared, and if our eyes had that capability, then we would see that the vegetation reflects most of the radiation back in the near infrared spectrum. So it's very bright in near infrared. And this kind of a variation as of the reflectance as a property of the wavelength, that is the main focus of hyperspectral remote sensing. On the bottom side, we can see that if we had a multispectral sensor like Landsat multispectral scan MSS or Landsat TM, then these are the bands. And so we have a lot of gaps in a multispectral sensor where we have no idea about the changes in the reflectance pattern. And these changes are required whenever we want to understand the properties, spectral properties of a material, as well as to distinguish different materials. So we can distinguish between a bare soil and a vegetated soil, as well as between different sort of a healthy vegetation from a less healthy vegetation. And so one of the resulting factors of this is that hyperspectral sensor has a lot of bands. So a normal sensor, let's suppose, has 5 bands. So your data is x comma y in the x and y axis, and the z axis in this data cube represents the number of bands. Then in a multispectral, let's suppose you have 5 bands, or even in case of Landsat or Sentinel-2, you have 10, 12 bands. But the same in case of hyperspectral will go from anywhere from 200 to 400 bands. And so the moment we have this many 400 bands, our computational complexity increases by a factor, multiple factors, because you go from 10 bands to 400 bands. So 40x is the computational load. And so, but it is of importance to have such kind of a data, because they can provide a lot of information that a multispectral cannot provide. For example, species identification in a forest, or exact crop identification with just one pass, which in multispectral you might require multiple passes, and still some crops like between maize and wheat, or between a few crops, it is not possible to do that, because the spectral properties are very similar between them. But for a hyperspectral, it is easier to distinguish. And they have a lot of applications also in the mining sector, also in the area of detecting some sort of a hazardous materials in case of a dumping site. All these applications require hyperspectral remote sensing. So right now we don't have a hyperspectral imager which is orbiting the Earth, at least in the public domain. But one of the sensors which will go up in a couple of years is this Copernicus hyperspectral imaging mission CHIME, and it will provide a lot of these data sets, and a lot of applications go with this. So for us, it is important to understand that for sustainable agriculture and food security, as well as raw material management, these sensing is of much importance to. A lot of other applications are there, right from understanding or detecting different gases in the atmosphere to coastal and inland waterways or cryosphere. And once this mission launches, again, we can see here that it will have a full spectrum range between 400 to 2500 with a bandwidth of less than 10 nanometers. So we will be able to see, let's suppose, the spectral profile of a mineral like kaolinite, which is shown here on the right hand side. And right now with Sentinel-2, this entire light blue color band is just one band. So the spectral resolution is very coarse in case of multispectral, but with hyperspectral, we'll be able to get a nice reflectance curve and identify the minerals as well. And so here I'm just listing a bunch of applications which are being done with hyperspectral, and which could be done at a larger scale once such missions are there in space. They go from things like LAI or nitrogen content to geology and minerals, or soil types and properties. So here is a beta testing version that has been created to emulate the canopy nitrogen content. So I'll not go into the theoretical aspects, but basically it requires us to do a lot of data processing, and so these huge data stacks are generated, which can be used to generate the CNC estimates. And this is currently being done using airborne platform, since the spaceborne platform is not yet ready, and these things are done. It could also emulate the leaf area index and as well as the changes. And so here we require that these parameters be included into a radiometric transfer model plus an emulator. and that requires a lot of GPU computations as well as a lot of memory computations as well. Now let's look at another example of LiDAR. So LiDAR are essentially an acronym for light detection and ranging, like radar is for radio detection and ranging, and it uses laser pulses which are thrown or which are basically sent to a target, and the reflections are basically measured. The time delay tells us at what distance that particular target is. There are two types of LiDAR, one is a point cloud and one is a full waveform. Currently, we have the Jedi mission, which is one of the two LiDAR missions which are currently active. The other one is ISAT 2. Jedi is interesting because it is not a dedicated, it doesn't have a dedicated platform. It basically is currently a payload on the International Space Station. And the advantage is that it flies at a much lower height at around 250 to 350 kilometers, and it is a full waveform LiDAR. So it divides its lasers into 6 beams. So we have here coverage laser and full power laser, and between each beam you have a horizontal distance of 600 meters. Each beam is 60 meters in diameter, so that's the spatial resolution. And between two beams you again have a 60-meter vertical, not vertical but along the azimuth, the 60-meter gap is between them. So essentially this is a sampling mission, so we will not have a wall-to-wall coverage, but we will have samples. And then that is where there are two things from a computation point of view. One is that since this is a full waveform, it provides a lot of metrics of the kind of a structure that is there of the target. Plus it even in a small area you will have more than 1 million points of this Jedi, which really is a very data intensive data sets. And so this is the kind of coverage that it is providing. So it started acquisitions in 2019, stopped in 2021, and again from this year it has started to acquire from ISS. So in the first 2 weeks it covered a bunch of area. In the 2 months it almost covered. So because it is on ISS platform, the coverage only is from plus 55 to minus 55 degrees latitude. Because it's a sampling mission, the important aspect is that we need to combine this with some sort of a wall-to-wall spatial data. So either from NISAR or from Sentinel-1 or 2 to get a wall-to-wall coverage map of the different parameters that it wants to invest. And these definitely require a lot of field data as well as a lot of ancillary data sets. So these are again computationally heavy data sets. So this is one of the preliminary maps that was generated from a year worth of data. And we can see here that these zigzag patterns, like a sweater, these are all the sample points that are there, and those are then converted into through models to the megagram per hectare of forest biomass that is there. And so these are one of the initial results which are generated from it. And we can see easily that most of the usual areas where high biomass is expected, like the Amazon forest, the Congo basin, the northeast India, as well as the Indonesian and Malaysian archipelago. These are the areas which have the densest forest in the world. And it is very important to detect any changes that happen through this. Also, using such data, we can also understand how protected they are and what are the challenges that face a person. So this is just the beginning in this series of missions which will basically map the environmental as well as ecosystems. And the missions that are shown in green, these are the missions which are going to be launched in the near future. So one of the ones which will launch very soon is this NISAR mission, NASA ISRO synthetic aperture radar. So the S band is provided by ISRO and L band radar is provided by NASA. It will launch somewhere in February next year, and biomass mission, which is a mission for tomography by European Space Agency, will launch in May. So these two are very exciting missions which will launch just in a few months from now. Now let's look at radar, which again is a very big data producer. So radar sensors are very important to get a lot of geophysical parameters as well as a lot of disaster parameters, in addition to all sorts of ecosystem and cryosphere biophysical parameters that are being produced. So just to give you a gist, when we look at radar, basically we are sending a bunch of radar pulses, and these pulses get reflected back from an area, and as we go on merging these pulses, we get a very clearer picture of what the area looks like. And so this is the synthesis across the aperture that we do, and that is what the where the radar goes from just being a radar to a synthetic aperture radar. So I'll just let this animation play through, and I'm hoping this is quite visible at your end also. So as you can see on the top right, the image gets clearer as more acquisition or more beams are being collated together. How does a radar imagery look like? So since we are hosting this talk in Mumbai, this is a radar image of Mumbai. It is quite different from an optical image. And you can see that the targets or the features on the ground are very different. So when we talk about radar, we basically are dealing more with the dielectric constant or the amount of moisture, as well as with the structural properties. So for example, the ocean that is there, the Arabian Sea, as well as the creeks, they are very black because these have a very high dielectric constant. So dielectric constant for water is 80, and they reflect off most of the radar radiations, and so they are reflected away. The geometry is important in the sense, or roughness is important in the sense that this X that is marked right in the center is the Mumbai International Airport, which basically has a very smooth tarmac, which is again reflecting off most of the radar. These three are the Powai, Vaitarnath, and the other lakes, which supply a lot of water to Mumbai. But you can see more importantly that structures such as bridges. So we can see this bridge, which is connecting, which is the new bridge that is there, not the ceiling that is there. This is a little older image, which is not very visible when we look at the optical image. But all the bridges are very visible because they are bright targets for a radar image. So different wavelengths basically have different sort of a penetration through the canopy, so or even a dry area. So one example which is cited a lot is this example which shows the paleo channel for a Nile. So I was mentioning about the shuttle imaging radar. So the image on the bottom is the shuttle imaging radar imagery colorized at C-band, and on the top is the photo taken from the shuttle with an optical camera. So mind you, both the image at the top and bottom are taken at the same time from the same platform. The top is an optical image, on the bottom is a radar image, which is given some colors. So what we see here is that this dark pattern, which basically is because of a higher water content in that area, and this is the paleo channel. So this is the channel that Nile followed, let's say a couple of hundreds or maybe a few thousand years back, and it still has a lot of moisture content because there will be underground water flowing through that. But the actual Nile channel flow is shown, which is again visible in the optical also. So this is how a lot of the discoveries about paleo channels are done, by the geologists. When we go to vegetation, the image at the top is taken from a C-band airborne platform. At the same time, the platform also took an image at the P-band. What is of interest to us and what is of interest to forestry persons who are detecting early changes is this sort of a linear feature that is there. And this feature, this is a part of Amazon where the image is taken. And this feature basically is an underground trail where the forest loggers have basically cleared a trail under the canopy, which is not visible at C-band because C-band has a wavelength of 5 centimeters. P-band has a wavelength of approximately 100 centimeters. So P-band is penetrating right through the forest canopy, looking at the ground, and it can see these changes that have happened on the ground. And what will happen slowly is that the trucks will come through this gap and they will start clearing the forest, and you will see a lot of deforestation. So these are early indicators of deforestation which are visible using a longer wavelength radar. If interested, right now we have the Sentinel-1 ALOS pulsar as well as UAV-SAR data, which is publicly accessible, and the data repositories are shown. Most of these are available from the Alaska Satellite Facilities DAC also. Processing most of this data can be processed using Sentinel Applications Platform, which is basically a European Space Agency platform. And you will find a lot of examples of how to process Sentinel data, which goes through these steps. And I have just kept one of the files that I found online, which takes you through the entire workflow of how to process a Sentinel data. Coming to applications, we understood a little bit about the using it for ecosystems or using it for some sort of early detection, but also a lot of other applications are there, especially ship detection. So recently there was a news that one of the startups in Ahmedabad is going to send a satellite especially for ship detection, and the way that they do it is ships are very bright targets for a radar because the background is the ocean, which has all the waves in it, which is basically a salt and pepper noise kind of a media, but the ship is made out of metal, so has a very distinct dielectric constant and dielectric property, as well as it basically is very distinct in its structure from the surrounding area, and so it is a very bright target, and that's how ships are detected. The other thing which is of much advantage when it comes to SAR is that the wake of the ship is displaced from the ship by the same amount as we can compute from Doppler frequency, which gives its velocity and direction. And so this ship, which is the wake is displaced by a lot, is traveling faster, while this ship, the wake is displaced shorter, is traveling slower. And so that's how we can get the ship's bearing as well as direction. Oil spills, because again oil has a different dielectric constant than water, so oil spills are detected, and this is one example of oil spill detection in Huntington Beach. So all this black areas that you see are basically the oil spill that is there, and this oil will move as the ocean moves, and so it will not stay in the one spot. So detecting such oil spill at a very high temporal resolution can aid the first responders to understand which areas to target and where the oil will move. Coming to the Indonesian as well as Malaysian areas, one of the biggest problems there is increasing conversion of equatorial evergreen forest into oil palm and acacia. Everything looks green when we look at the optical image, but when we look at SAR image, the oil palms are very distinct from the surrounding forest because of their distinct structure, as well as because they are planted, and so it is able to detect them. Similarly, as we saw earlier, these forest tracks lead to deforestation, and we can track whether there is a non-forest growth or a regrowth in that particular area. Agriculture, we basically are doing operational license mapping that is being done using SAR. And then coming to high-end structure, here technique called tomography, which comes into play. Further, whenever we talk about flooding, one of the major things which cannot be detected is subcanopy flooding, wherein the floods occur under the canopy, and it can basically destroy the vegetation underneath it if there is a prolonged flood, but it can be mapped using the SAR. And also for geologists, subsurface mapping, paleochannel mapping, these are all processes which are also possible using such data sets. Then there is a very highly advanced technique which is called as interferometric SAR, which is able to measure the displacement of a target even by a few millimeters. So this is an example of subsidence mapping of Berlin, which was caused because of the underground tunneling done for its metro expansion. And what it shows here is these areas in red basically have an upliftment of 6 millimeter per year, while the areas which are basically in yellow have a slower upliftment. So there has been some upliftment in some areas, and these darker blue areas have a subsidence going up to 6 millimeters per year. And so these have been done over a period of 8.5 years. It's a long time series data which has been processed at a very fine scale to provide such subsidence information. Uh, Also, since it can do subsidence, it definitely can detect earthquake deformation. And here we can see the deformation, and these are the fringe lines. So between each of the blue to blue of the red to red is one phase displacement, which can be converted into the actual displacement based on the baseline at which the two acquisitions are. And more importantly for the geologist, the area between this is where the displacement has started to occur. So this is the epicenter of the earthquake, and so these can be detected. And also vertical motion tracking, like we did with subsidence, we can also understand whether a dormant volcano, is it moving, and is there a imminent danger to the people who are staying closer to the volcano. So this is an example of Mount Etna, the example shows. Now, we have given a fair bit of a time to understand some of the applications of this geospatial data, where it comes from hyperspectral or LiDAR or radar. And there are a lot of applications which require a lot of time series data or a global understanding of the data product. And that is where the need for scalable geocomputations comes in. So what is increasingly happening is, like with any sort of a data that we are basically ingesting, be it mobile data sets or social media data, we are getting a data deluge. And in this data deluge, one thing is getting information, and because since we are all in some way going to analyze this information, we want platforms to do this analysis rather than our own computing needs. So there is a lot of data that has been coming in. So if we look at just the phase-bound platforms, terabytes of data is coming in daily, and which is predicted to just increase as we go further. So if we look at just the NASA side of the things, there are around 13 DACs which are currently there, which are hosting a bunch of data. ISRO is also hosting a lot of its data in Bhundi, but it is just really limited to most subcontinent. The global products are available from other satellites, which basically cover the entire globe. So if we look at just the two missions which are have already launched or going to launch, so SWAT and NISAR. So SWAT launched early this year, and NISAR will launch next year. They are going to produce 100 terabytes of data daily. And so this is just the raw data. This doesn't even include the processing that will be done on this data so that we can generate the data products in level 2 to level 4 kind of a geospatial data. And currently, just NASA's Earth observation data sets is around 40 petabytes. So that is 40,000 terabytes. And so that is only going to increase as more satellites will be put into orbit. A private company like Planet is also producing around 10 TB of data per day, and their satellite suite will increase. And so we will have in future explosion of this hyper data sets as soon as more LiDAR platforms, more hyperspectral platforms, more constellations from companies like Planet will come into play. And just to give an example of the amount of data we have, it's not just that, okay, NASA has petabytes of data, okay, fine, but why should a normal person be concerned with that? One of the ways in which it can be shown is through this chart, which basically shows on the x-axis the year, and on the y-axis is something interesting. So this is the bytes of data that you get per hectare. So if, let's suppose, you are a person who is studying agriculture or applications in agriculture, you are interested in 1 hectare of agricultural data. If you talk about Landsat initial series, then you're only dealing with a few KBs at max of data per hectare because the resolutions were very coarse. As the resolutions have increased, as the number of bands have increased, as the kind of satellite sensors have diversified, the amount of data that you're getting in just 1 hectare has gone from a few kilobytes to now more than 100 megabytes. So even if you are only interested in a very small area, let's say just one state, one district, then also you are indulging into at least a few gigabytes of data per acquisition, per sensor. And nowadays, increasingly, we deal with multiple sensors at times, series of acquisitions. And so we need a lot of data to process, or at least we need ways in which this can be done, even though at our local level, but it should be still scalable. So if your algorithm works at your local, let's say Jupyter notebook, it should be done in such a way that it uses things like, let's say, Dask or X-arrays, so that if tomorrow you get access to a server which can process the global products, then it can easily scale up. A lot of this also is dependent on the amount of information that we are trying to extract. So let's take example of forestry. We initially were content with understanding just, let's suppose, the type of forest that is there at different. So let's say Landsat or Sentinel was fine. But now we want to have their structure, we want to have the biochemical properties, biophysical properties, we want to get it not just monthly, we want to get it weekly or even daily, and we want it not at 100-meter resolution, but at 1-meter resolution. So our demands on the spatial resolution, the temporal resolution have gone up. The demands on the kind of information that we want from a specific target have gone up. And so have acquisition cost and the processing cost. Some of these satellite sensors are free. So let's say you are only interested in NDVI, LAI at a fair enough resolution. Landsat or Sentinel will be fine for you to get a 30-meter or 10-meter. But the moment you want it, let's suppose every day, okay, then we are looking at a planet kind of a data sets, which will have its acquisition cost as well as processing cost, because it is going to provide you a lot of data. Then when we go into the structural and biochemical properties, we want to go to radar, we want to go to LiDAR, we want to go to UAVs. The moment we go into UAVs, then the acquisition cost shoots up, the processing cost also shoots up. And so that is where geo computations get increasing. So looking at all this, what is needed? So a little bit I want to spend about the open source, open platform, and what we essentially are aiming to do as a community is we want to democratize the data and provide not just the data, but also the analytical power to all. So let's just give the computational power or the process in which the data processing can be done at a user end. And one of the earliest ways in which this started was Google Earth Engine, which basically gave a ability to anybody with a little bit of Java code to open up the available data sets. But let's give a few minutes to understanding what is open source and what is open science. So the vision for open source science in a way is to expand the participation, improve reproducibility, and accelerate scientific discovery for societal benefit. So it should not be in the few hands that large amount of data processing can be done and nobody else can replicate it, because unless we reproduce or replicate a result, the basic motive of science is not satisfied. And so that is where this sort of open source science is required. These are the few things that I have taken from the NASA's objective to do open science. And basically it involves into getting a larger scientific community as well as wider public accessibility to understand scientific research as well as help accelerate it. And that can only be done when we have a collaborative culture, which is empowered by open sharing of the data as well as the processing power. There are two meanings of open in open science. One is just transparent science, which basically we do by publications. We share the process by which some result has come up, make it accessible, make it understandable. But the more important is getting inclusive science. So it makes little sense to a person who doesn't have the ability to reprocess the same data that they see in a scientific paper, unless there is an inclusivity where the processing power is also provided. So it basically comes up with these four things, pillars. Let's suppose it should be transparent, it should be inclusive, it should be accessible, and it should be reproducible. So we are in somewhere on this line where we are going from a fully closed system where the public has no data access, no publications, to having a little bit of more data access, some free data. And slowly, hopefully, we will be moving towards a lot of free open source data, open source software, open source algorithms, where reproducibility can be obtained completely. And so that is a fully open data set. It's a far away, but we are somewhere in between, more towards the darker green side of the spectrum. When we go through this, the evolution is that we open the, let's say, the code to it, and then it can be deployable by others, it can be developed by others, and then the community as a whole goes into development. And so this leads to building a complete ecosystem of science, which will help initiate new missions, because as more people understand the outcomes of a particular algorithm or a particular platform, then we can have more clear policies on how to improve it and how to build upon it. So now coming to some of the tools in which this can be done, is one of the common ways is to have a common metadata repository and also have a distributed archival platform. So a lot of DACs come into it. Currently under active development is this multi-mission algorithm and analysis platform, which will provide a cloud-based environment to process, analyze, and also share data sets, as well as to put up algorithms on it. And then hopefully we will also go into some sort of a policies which are more open source and open data accessible. What will this do is it will basically focus the open science tools at the center, and which will provide us with a lot of products which are generated because of these practices that will evolve with time. Now coming to the some demonstration that I'll show for map, but before that, if because since map is still something which is under development and it's completely not open to public, hopefully next year it will be made public to more beta testers. If you are using Python, then one of the ways is to use Dask or Xarray. So I'll just give you a brief on Xarrays, and there is something called as Xarray Spatial, which is a raster-based spatial analysis in Python, and you can just import this in Jupyter Notebook and process it. And what it does is it can provide you with a bunch of tools which can provide focal analysis, multispectral analysis, and these all are done using Xarrays at the backend, and they are also capable of converting that into a GPU processor. And a lot of topographical analysis can also be done. So example is slopes or terrain generation, viewshed generations, aspect, and so on and so forth. Right now GPU Dask data array is not possible, but with Dask it is possible to generate all of these. And what it does is it basically is tying up a lot of these different platforms or different packages that we use with Python, which is Xarrays, raster.io, GDAL, QPy, Dask. So QPy is required if you want to process with CUDA. Pandas, excellent tool for tabular data analysis. And then we have spatial pandas like GeoPandas, which can run with shape files or any sort of a geospatial data set, as well as Shapely. So all of these in turn can be used with this Xarray Spatial. And this basically what it does essentially is, let's suppose you have a data set of 10,000 by 10,000 rows and columns. It basically divides into chunks of, let's say, 500 by 500 and processes all of them in parallel. And that parallelization, even in a decent system, let's say having 8 cores and 16 threads, so you can easily have 16 parallel processes taking place instead of the entire 10,000 cross 10,000 matrix being ingested directly into the RAM. And that is what basically improves on the processing capability. Now I'll come to a demonstration of map. So first of all, I'll give a brief on what is this. So it's a multi-mission and algorithm and analysis platform. It is a joint development that is currently taking place between NASA and the European Space Agency. It is a virtual environment dedicated to sharing of the data as well as to its processing. And basically it has a science focus to improve the understanding of global terrestrial carbon dynamics. And it basically involves the use of Jedi, which is from the NASA side, biomass mission, which is from ESA, as well as NISAR, which is joint mission between NASA and ISRO. So there are three goals. The first goal for this platform is to give accessibility to the data. So it will provide seamless open access data set to the airborne platforms, spaceborne platforms, as well as field data for biomass mapping. The airborne platform will typically use the UAV SAR platforms as well as its data. Second is rapid algorithm development. Uh, it has the ability to upscale users' algorithms. So we go from a Jupyter notebook to a area where it is processing for the entire globe, and it will provide a collaborative environment. So where it is very distinct from, let's suppose, a Google Earth engine, is that on Google Earth engine you only have access to a certain level of data. So for example, in case of radar, you only have access to the amplitude of the radar data, not to the phase information, which is a very process heavy task. While on map there is no such restriction. It accesses the raw data directly, and you can do whatever you want with it. And so you can first of all build a Jupyter notebook, because everything works in Python there. You are not required to learn anything new. Process it on Jupyter notebook for a small area, and then upscale it so that it runs basically on the entire globe. Now, when we come to the architectural capability, it has a algorithm development environment, ADE, and that is where the algorithm developers like me or the science team members like Marco, we come into play. We do the product validation, and we are using these notebook containers to do this. Once we have this, we can basically convert the Python Jupyter notebook into a Python code which works tile by tile, and we can then use a data processing service. So this is a service wherein, let's suppose I request that this process at 1 degree or 1 degree tile be run for the entire globe. So it will basically call up instances of computing on the cloud, which is basically it will fire up multiple processors, and it will process that data. So it will call up the data from the standard products from European Space Agencies or NASA archives for now, and those products can directly be accessed into this analysis ready processing workflow. The products are generated, and that can be stored, as well as it can be optimized to whatever way we want. So it can be converted into a OGC WCS file, or it can be a cloud geotiff file, and those then can be given as an output to a person who is requesting that. Where this is very distinct from the other such platforms like Google Earth Engine is that it not only has an algorithm development platform, which is shown by this purple over, where basically we have the ADE as well as the DPS, but it also has an analysis platform where once this product is generated, then it can be further optimized, it can be further provided as a value addition products. So I'll play this recording, which is from mapping AGB with L-band backscatter, and you will hear the voice of Marco and me in tandem, where we explain how we develop and assess new biomass mapping algorithms for preparation of this NISAR mission.
Sir, your voice is not audible. Unmesh sir, your voice is not audible.
Hello, sir.
I think sir is not in meeting, sir. Sir is not there.
Yeah, I called him.
Yeah,
I
join.
called him. He
Yeah,
is back.
just now join.
Uh, Hi. Sorry, I had a connection error from.
Yeah, yeah, sir. No issue, sir.
No
Please
issue.
share your screen.
Yes. So please let me know where the video was playing when it was there.
No.
No, sir. No.
No, sir.
Okay. So please let me know if you are seeing this.
Yes, sir. Yes, sir.
Okay,
Yes.
perfect. So basically, in this NISAR, we will, when the NISAR mission comes in, we will have a lot of data products. So the level one data, which is shown here, will basically have 25 terabytes of data, and then level 2 and level 2 GCOV, which will be another 25 to 30 terabytes. And it will provide with a very fine scale resolution data at 10 meter or finer at every 12 days globally. And so a lot of these data product will be generated. We go here on step by step into how on map platform we are able to process for biomass mapping. So an example is shown here where we are right now accessing Alos Pulsar tiles. So these are 1 degree by 1 degree tiles, and as we browse through this map portal, we can see that these tiles basically start popping up. Each of these tiles shown by this green square is 1 degree by 1 degree, and we can select as many tiles as we want, or we can basically select the tiles for the entire globe would be basically covered by this. And so once all these tiles come up, then what can be done is we can go to the algorithm where in the Jupyter notebook basically works for one tile, and then we go into the DPS. So we'll go into that processing in a minute. So here we basically use a Jupyter notebook to display the way in which the biomass is estimated. So we are using here a modified water cloud model to estimate the AGB using backscatter. And so here we can see, here we are downloading one single granule for this. Once we have this granule, so this is the local path towards this granule, and we can then provide, the user can provide the input granule. The map will download this granule and will process using this plant toolbox, which is again a JPL developed toolbox. So here we show a dummy algorithm which basically will convert this L-band backscatter on the y-axis to the biomass on the x-axis. So a WCM model typically follows such a curve where the backscatter, which is the measurement from satellite, is converted into the above ground biomass, which is the measured parameter on the ground. And so we can see here that we are using here tools such as GDAL as well as a bunch of other tools to process this data, and a simple matplotlib will basically help into plotting these data sets. Now, once we have the granule, we can show within the same map environment of how this granule looks as it is overlaid into the on the base map. So here the darker greens means higher biomass. So we can see that on a axis of 0 to 300, we can basically have mapped out the biomass content for an entire 1 degree by 1 degree tile. And so at a very extremely fast pace, we have processed 1 degree by 1 degree, which is approximately 110 kilometers cross 110. Now what we can do is we can go and execute a DPS job. And so this is the data processing scheme, and I have already converted this Jupyter notebook into a Python tool, wherein the only thing I have to mention is what is the minimum and maximum lat long on which I want to run it. So for example, globally, if I want to run, I would just put it at from -180 to +180 in the longitudes and -90 to +190 in the latitude. Now here I run it live and I get a job ID. Now this job ID, basically I can basically go back to this DPS UI menu and go to this DPS jobs UI, wherein I can see that this job is queued. And so this queued job means that it will run as soon as the other jobs process, and depending on how important it is, it could also skip the queue also. So once this job runs, it will, what at the back end it is doing is it is downloading each and every tile. So across -180 to +180, and from North Pole to South Pole, we approximately 1100 tiles. It will generate those tiles, and then I can generate a virtual raster table, VRT, over that area. And so just to save time, I have already downloaded it here. And so this VRT is generated for this JAXA FNF. And I can share this with anybody with a pre-signed URL. And so once you have this URL, you don't need any separate access. So it is access control free for anybody to view this URL to get the VRT access, and then basically get an access to the entire global product, which is generated within a very short time. And so here we can see the VRT information as well as I can display it. So here we are displaying the entire global product, which is on a folium. And here we can see the global biomass product. Now, mind you, this is generated as a dummy, so Greenland is also popping up there. But once we can also put in for each tile what is the land use, land cover, and only process those areas which have forest, then all your areas which don't have forest will not pop up as much as they do pop up here. And we can go and zoom into any particular area, and since it will be generated at its final, at its resolution, the product resolution will be the same as the tile resolution. So the tile size is 1 degree 1 degree, but the resolution of JAXA FNF is 100 meters. So all the products are generated at 100 meters. And this is one of the ways in which a really powerful platform can be used to basically process the any sort of a any sort of a mapping that can be done for the entire globe. Now, a little bit more, we can basically look at the Congo Basin and look at all the features which are there, as well as we can go and look at a very smaller area. So this is the Gabon forest, which is near Libreville in West Africa. And we can see the kind of a spatial detail that we are looking at. So this is one of the highest mangroves forest in the world, which is exceeding 90 meters in height, and a very dense forest. A lot of it is mapped using these AFRISAR missions, which are, and also DLR-FSAR missions, which flew a lot of sensors on these areas. And the most important thing for us when we talk about geo-computations is the processing time. So if you look at the left-hand side, this is processing one granule. So 1 degree 1 degree, it took approximately 16 minutes. But the ability of scalable geocomputing is that we can run, let's suppose, even 90 or 100 machines in parallel. Then if you look at the entire world, it took us barely half an hour to process the product for entire world. However, if we had processed it individually, it would have taken approximately 12 days, which is weirdly the same amount of time that NISAR will provide a new acquisition in. So the temporal resolution of NISAR is the same that it will take for a normal computer to process the global data product. While here, if you use a scalable geocomputational method model or algorithm, which will work in a platform like MAP, then for the entire globe, 20-30 minutes is the time which is required to process this entire data. And for a continent even of the size of Asia, it only takes around 12 to 13 minutes to process this data. And so that is where the advantage of MAP is. Now, the workflow essentially can be shown like this, where we have the user to provide the bounding box, and then the control algorithm, what it does is that it will basically have multiple granules, and it will query the granule. It will see if it has been already taken up by other processor, and then it will basically go through the entire process, that it will download it from the data repository, and it will provide you data products, and then each of will again be converted back into a TIFF and a VRT, which will be provided. And you can also generate this VRT cloud scalable format, which will basically vary at different resolutions. And so we have already seen that the advantage of time that is there in this particular area, and then the example of the product which is generated. Now, it is not only a dummy product which is generated, but recently they have also launched an entire boreal biomass product, which was also highlighted on the NASA portal. And where we're going to go from here is we are increasingly looking at creating digital twins of each and everything, which basically requires a lot of these extreme scale capabilities of processing at large scale, as well as have understanding of the properties, as well as how the medicine. So, in summary, using geospatial data that is available, there is a understand the scalable geocomputations. This can either in a local server with a script or task or Uh, hello, hi. I hope at least I was able to show some of it, because I again lost.
Sir, you can share the screen.
Okay. Were you able to see the processing?
Sir, we are not able to see your screen.
No. Where did I drop off? I just wanted to know that. Was this screen visible earlier?
Yeah. Yes, sir.
Yeah.
This slide we have
So
done, we move to the next slide. Yeah.
okay, perfect. So I think I'm just about to conclude, and so basically, it's not just dummy algorithms which have been tested, but a boreal wide platform has also been product has also been generated by this, and which has been already launched on the both the NASA as well as ESA platforms. And where we go from here is we want to essentially go to generate digital twins of each and every target that is of interest to us, be it agricultural crops or be it buildings. And that requires a lot of these supercomputing as well as extreme scale capabilities, one of which is the geocomputational capabilities that can be provided. So in summary, with the amount of data that we are generating, especially from space as well as from UAVs, there is definitely a need to understand scalable computing and also to provide a way in which it can be done. It could also be done with local servers or with Dask and X arrays, or it can also be online from platforms such as GE and MAP. And so this is in conclusion for this talk, and I hope uh, the way in which map I could show how to process large amount of data, it was some sort of useful to understand what can be used to when we generate global products. And so that's it from me. So I open up the forum for any questions that you might have.
Thank you, sir. Thank you so much, sir, for sharing the valuable insights with us. Now it's time for us to engaging in our question and answer session. The sir has already told you. So this is your chance to ask any questions you may have regarding the topic discussed. So feel free, participants, to ask the question.
Hello, sir.
Yeah, hi.
Sir, which type of data is suitable for SIP detection?
Ship detection SAR data is suitable because it has the ship has a very distinct structure as well as nature with respect to the background. So you can do that with Sentinel data sets as of now.
Is it level 1 or level 2, sir?
Level 1 will be preferred, and then you can process it to your area and generate GRD data sets from there.
Okay. Okay. And sir, another question is that this map is available for everyone.
So right now it is still in the beta testing phase. So to some of the testers and developers, it has been made available, but it is not yet public. So hopefully once NISAR launches, they will host some of the algorithms on it. And the idea is that it will be made public, although with limitations on the data analysis part, like how much data you can process freely.
Okay. So for level 1 GRD data, is it speckle filtering is required, sir?
Uh, for ship detection?
Yes, sir.
Yes and no, both. You can directly also use without speckle filtering but ideally, yes, if you use a refined Lee filter, that can be one of the ways in which you can reduce the clutter in the background. It also varies a lot with the nature of the ocean. So if the ocean is calm, then your ship is much easily detected. If the ocean has a lot of waves, then that can give some spurious signals also.
Okay. Sir, other than Snap, any other tool for this kind of applications?
So right now, Snap is the ideal one, but there is another tool which is called as ICE3, ISCE. But that's a command line tool which is developed by JPL, and it has the capability to process Sentinel also. Other than that, there are a
Okay.
bunch of like MintPy kind of a tools which are generated, but the globally available with most documentation is Snap.
Okay, sir. Thank you, sir.
Thank you.
Anyone else?
So, good evening, Umesh. Your presentation is really nice. I enjoyed the
Thank you.
presentation. And to start with this Python kind of work, can you suggest me some materials that will be helpful for a beginner?
So Python essentially any code that you use where it is directly, let's say, ingested with a NumPy array. One of the easiest ways to start off is to convert that into an X array. So if you just go to any tutorial on X arrays, that it basically gives you an idea of how to ingest, let's say, at 512 by 512 kind of a area. So only 512 512 pixels will be ingested at once, and it will dual block processing. So that will be one of the easiest ways to start off with scalable geocomputing. You can do it with your own laptop also. It doesn't require that you need to have a server. And then slowly you can move to Dask. So XRAs will be one of the easiest ways to start off.
Okay, thank you.
Sir, is it possible to share your studies slides with us?
Yes, but I will have to remove the recording because that I don't have the permission to share. I can share the rest of them with Dr. Prakash, and they can share with you.
Okay, sir. Thank you.
Thanks.
So we are done with the question and answer session. So now it's
Okay,
time to
thank you.
express our sincere thanks to our eminent expert, Dr. Anmesh sir, for his insightful presentation and demonstration session on scalable computations for geospatial data. We request you to accept this virtual memento as a token of appreciation and gratitude, sir.
Thank you so much. It has been a real pleasure to talk about this.
Thank you so much, sir. We are truly grateful for your time and expertise that you shared with us. Your sessions give us a lot to think about various aspects for remote sensing, multi-mission analysis algorithm and analysis platforms, and various applications on scalable computations for geospatial data. Thank you so much, sir, for your insightful session.
Thank you. Thank you so much for having me. Have a nice evening, everybody.
Yeah, sir. Same to you. We'll be in touch with you through email, sir.
Definitely, definitely.
Yes.
Thank you.
Thank you so much, sir, for joining us.
Thank you,
Now, I am one
participants.
announcement is that all are requested to fill the attendance as well as feedback link is shared in the chat box. Thank you, everyone. Thank you once joined the session. Tomorrow on the same time, we will start the session.
Yeah, tomorrow we'll start at 6 p.m. So the
Yes.
directly we are starting with our uh, speaker session. So tomorrow, please join at 5:55, 5 minutes before. I request all the participants to join with the registered email ID. So otherwise, it will be difficult to accept each and every one if you are using the different email IDs. This meet will be there for next 5 minutes, and those who are not filled their attendance, they can fill the attendance. After 5 minutes, we'll close this meeting.
Yes, Sonali ma'am, have you asked something?
Yeah, you have in doubt. Yeah, whatever you are registered through ATAL. So ATAL email ID is there. You have to use. So what we'll do tomorrow, we'll send a list of participants with their email IDs, what we got from the ATAL, so that accordingly you have to use the email ID.
Prakash sir, will you able be share to this recording to with us?
Yeah. Once we have done with all 6 day sessions, we'll share all the material along with the recordings through our registered email ID, and you will get all the links there.
Okay, sir. Yes, sir. Thank you.
Yeah, definitely. Thank you, ma'am. Thank you, Ekta ma'am.
Thank you, sir. So we can close the meeting.
Yeah, for next 5 minutes, we will keep it on because some participants have not used the attendance link to fill. So for 5 minutes, we will keep it and we'll
Yes, sir.
close it.